Hello, class. Welcome to this week where we are going to talk about something called inference to the best explanation. This is a kind of inference we make. In order to make that inference, we need to know a little bit about explanations so that we can tell when one explanation is better than another kind of explanation. So let's dig into it. All right, so as mentioned, we are going to be talking about inference to the best explanation this week. And in subsequent weeks as well, it will come up. Now, there are many kinds of explanations. You might just think of a procedural explanation. Someone might try to describe how to ride a bike, right? You have to have enough forward momentum to keep from tipping over, unless you can do a track stand or something like that. So you have to pedal, you have to steer and make adjustments and so on. But that's a procedural explanation. How to make a cup of coffee, how to print to a cloud printer, what have you. Some explanations are interpretive. So here you might think someone my age might say, hey, what is it that the kids say these days? And someone might give me a term and then explain it to me, right? This is what is meant by a use of that term on some occasion. And I might say, right now I know the meaning of that term. But that's an interpretive explanation. Sometimes we look for interpretive explanations when we're doing a little analysis, right? We might read a piece of poetry or prose and want to know what the author intended, what the sentence actually means, perhaps despite the author's intent, and so forth. But those are all interpretive explanations around the meaning of terms in a language. And there are also functional explanations, right? Someone might just want to know how something works, right? So maybe not how to do something, but someone might say, what is it that this button does here? Or what is it that this particular menu item does in this application we're looking at? And I might provide a teleological or functional explanation of that thing. I might say, this is the goal, that's an end result, and doing this thing gets you that goal, right? Push this button, get that. We, this week are more concerned with scientific explanations, right? We want a theoretical explanation. So it's these kinds of explanations, at least that many people think, shed the most light onto a given phenomenon. Typically, they will use hypotheses or theories to explain things. We won't fall into the trap of thinking that all theories are equal, but nonetheless, we will need to make some simplifications in order to get off the ground. So let's just see what these look like. I don't want to get too lost in the weeds when it comes to the structure or the form of a scientific or theoretical explanation. And many theoretical explanations, when they're offered, might not give you all of these parts. But if we were to reconstruct what a plausible explanation of some phenomenon might look like, this is how we might think about it. And this is just the structure first pointed out by the philosopher Karl Hempel. So explanations have two parts. There's the explanans. Think of those as the premises if we're thinking about an analogy to arguments. And then there's the explanandum. Typically, that might be some event that we're trying to explain or some phenomenon. And we can express that with a statement, like you see on your screen. B occurred, where B is some event. So it could be that I want to know why my beloved Toyota Prius is on fire today, right? I might say, oh my goodness, right? Like my car is on fire today, April 1st, and it's not a April Fool's joke. Well, if I want to know why my car is on fire, I'm going to need an explanation, right? Right now, I am puzzled. Once I have an explanation, then it will seem very likely that my car is on fire, given what I now know. But without the explanation, it's a mystery. That is what good explanations do. They remove the mystery around things. So my car is on fire. That will be my explanandum, and I want to explain it. So maybe I need some theory about what it takes to have a fire. So if I oversimplify a little bit, I can say, look, in order to have a fire, you need three things, right? You need an oxygen-rich environment, you need a fuel supply, and you need a spark, right? You need a source of ignition. If you get those three things, you get fire. But that, just the law by itself, or the theory by itself of fire, doesn't say why my particular car is on fire in this particular moment. So somehow we have to connect that general theory of fireness to my car. So if you know when there's a spark, and you're in an oxygen-rich environment, and there's fuel, you get fire, suppose also that we then learned that evil Joe, who's got it out for his old Professor Horton, struck a match near the gas tank of my car. Well, my car is in an oxygen-rich environment. Gas tanks typically have fuel in them, and matches are a great source of ignition. Gas, oxygen, spark, kabooey, right? My car is on fire. So with those two things, now that you have your general theory of fire and some particular facts about Joe, that then makes it very likely that your car would be on fire. After all, if you knew that Joe did those things and you knew how fire worked, it would no longer be a mystery. You would expect fire. In fact, just reverse it, right? Instead of someone telling me my car is on fire, imagine someone came in and said, hey, in order to have a fire, you need a spark, fuel, and oxygen. And guess what? Joe's outside right now throwing lit matches into your gas tank. What would I expect, right? Fire. So there's a logic to good explanations. And you can have competing explanations for the same thing, right? Sometimes we may not know what the best explanation of a particular phenomenon is. And we say, well, what are the top 3 contenders, right? What could it be that explains this thing I'm trying to explain? Well, this is where an inference to the best explanation comes in. If, and I'm going to tell you how in a minute, but if we could figure out that one explanation really is better than the others, then we could infer that that explanation is likely true. That is how an inference to the best explanation works. So we have some phenomenon Q, Horton's car is on fire, let's say, and maybe the Joe strike a match theory is the best explanation for my car being on fire. Well, then we might infer that that explanation is probably true. Key word is probably. We might also use this in real-world simple cases, right? Maybe Maria's absent, and there's a hypothesis that she overslept because she's known to do that. Well, it's probable that she overslept, right? It's not certain. I could be wrong. But if that's the best explanation going, that's what we should believe. We are justified in believing the best explanation when it really is the best. Now, we can't cheat, right? We can't stack the deck in favor of our favorite explanation. We have to look at the criteria, determine which explanation really is best, and then go from there. So what are those criteria? Well, at a minimum, an explanation should be at least internally consistent, which is to say free of contradictions. Almost all theories pass this test. Some very famous logical theories sometimes may not pass this test, but for the most part, a scientific theory will pass this test, at least in most obvious cases. And externally consistent just means it's consistent with the data, right? If you have a theory about water that implies that water is wet, implies that water is not wet, then that theory is not externally consistent, right? It doesn't even fit the data you're trying to explain. I'll kind of give you an example of that later. But this is a minimum condition before you even get off the ground. Check to make sure your theory is consistent, and we will get there. Here are our 5 big criteria. These are the ones that we're going to focus on mostly in our homework and in the discussion forum. Testability, fruitfulness, scope, simplicity, conservatism. I'm going to explain what each of these is in turn, and then we will get to work. So first things first, a theory has to be testable. If I can't generate some observation that directly or indirectly bears on the truth of a theory, then stop right there, right? The game is over. There is no confirming or disconfirming the theory. Why should I believe it one way or the other, right? Set it aside till something happens. Sometimes theories are not testable in practice, even if they're testable in principle. Albert Einstein's general theory of relativity made some very specific predictions around how light would move near massive objects, but when those predictions were first noticed, they could not yet be tested, right? We had to wait around, and I'll show you a clip of this in a second, for Sir Eddington to conduct his famous experiments. So we have to at least be able to say what it would take to confirm a theory. Could be direct observation. You literally see something that confirms the theory. Could be indirect observation, where you connect some theories' unobservables to something else that is observable. So take just as a quick thumbnail example, something like a black hole, right? Black holes don't emit light, even if they might arguably emit some other things. How do you tell whether they're there? Well, you can connect the unobservable dense mass that is the black hole to other things. And then you go look for those other things to provide indirect confirmation for the existence of a black hole, let's say, just for example. Okay, so theories have to be testable. Sometimes 2 theories can be testable. How do we tell then, right? If you could test them both. Well, you could just go start testing them and see which turns out better. But a second criteria might say, let's look at a theory's fruitfulness or an explanation's fruitfulness. Some theories make new predictions that have never been made before. And when those turn out to be true, that is really good news for that newer theory over the older rival theory. And this is exactly what happened to Albert Einstein's theory versus the much older Newtonian physics. Newtonian physics was great. Newton was a really smart person. He was one of the independent inventors of calculus, along with the philosopher Leibniz. Super smart guy, had a great physics. It's false. Why do we think it's false? Well, he predicts that light would not bend around massive objects. Einstein predicts light will bend around massive objects. That is a new prediction that up until then had never been made before. Turns out Einstein was right, Newton wrong. Both theories are testable, but Einstein passes the test in a novel way, right? It's a brand new prediction. It's one thing for theories to make old predictions that we already know. That's not all that exciting. But when a theory comes along that can get the old stuff right and make new predictions, we tend to think it's more and more accurate than the theories that went before. That's called fruitfulness. Now, in all but the most common cases, this will be sort of plain as day, right? When some new theory comes along that can explain something. We might learn a new cognitive bias, for instance, around human beings, and that could explain why certain people continue to believe there's such a thing as being hot in basketball, despite there being very strong evidence that an effect is almost negligible. Why can we explain that? Because we know how human cognition works, right? So that's just a fact about cognition. That is a new fact about cognition, right? That fact would not have been predicted, let's say, 100 years ago, but now it is. That's good for our theories of human cognition that treat human beings in a certain way, bad for theories that don't. So we'll get to talk a little bit about this. It will not be our focus. We're not doing science this semester, but I did want to point out fruitfulness. And here's what that might look like if you just want to see the prediction that Einstein made. If you were to think about where the stars are in the sky, you can say, and the stars, relatively speaking, don't move all that much, right? You could go out tonight and put an X on a sky map for a star and go out the next night and it will be pretty much in that same spot. Planets, of course, are not like this. So if light bends when it passes by a massive object, you could take the light coming from that star and just wait till daylight, which is to say now the sun is in between that star and us, and look to see what happens to the light. But it's really bright during the day, and so you can't see stars during the day. How do you tell? Well, this is why Sir Eddington in 1919 waited for an eclipse. Once the eclipse was there, boom, sun's blotted out. Now you can see the light coming by the sun from those stars because it is not being blocked by the moon. And guess what happened? The curvature of space-time, or the gravity of the sun, was pulling that light from the stars in, which made it look as if those stars were much farther away from the sun than they were, right? If it bent the light from the star, then you can look at the dash line. It would look as if it's coming from there, even though it's not, right? Without the sun, the light from that star would shine off over to the left, but because it's being pulled, it's looking like it's coming from a different spot. And here's an actual, I used to have an actual picture of that experiment in my slideshow. I don't any longer. But if you're interested, just Google Sir Eddington 1919. That was the year he did the studies. You'll find all the pictures you need. They're pretty great. The third criteria. So far, we want theories that are internally consistent and externally consistent. They fit what they're trying to explain. We want theories that are testable. That's good news for a theory. And we like theories that make new predictions, especially when those new predictions come true, right? We also want theories that are broad. Think about why scientists might talk about a grand unified theory. Well, if we had one theory that could explain the quantum realm and could also explain really big objects, that would be great, right? One theory is preferable to two, especially when those two contradict each other. So one theory is better than two when that one theory can explain all the things that two can. That's because it has broader scope. We like theories with broad scope that can explain lots of things and not just the original thing that they were introduced to explain. This is where some theories tend to flounder, such as like the flat earth theory or maybe UFO sightings. A theory of the heliocentric model, right, where the earth is not at the center of our solar system, it is rather the sun. That theory not only, at least at the time, explained the things that we already knew about how planets move and so forth, but it got some new things right. Right? Those were good things about the theory. So it was broad scope, right? It made new predictions for one, so it was also a fruitful theory, but it also had broad scope. It could explain other things that we observed about the solar system that the previous theories could not. That gave it broader scope. Or think about UFO sightings, right? So Well, let's look at competing theories, right? So here's one theory of what could be going on when people claim to see UFOs. One theory is that they really are seeing aliens from another dimension or galaxy or planet, right? If aliens were real, that would explain alien sightings if those aliens were visiting Earth. Theory 2, human perception plays tricks on us. So that's another theory. Now, what can a theory of human perception explain? It can explain human perception, right? It can explain where our memories fail. It can explain why I remember some things better than others. It can explain why McDonald's are painted the colors they're painted, right? Because of how our perception works and what colors we're naturally drawn to or what colors stick out to us. A theory of human perception could explain those things. How could it also explain UFO sightings? Well, our minds are primed to see patterns in the myriad, manifold of experience, if you want to put it that way, right? We're getting bombarded with perceptions all the time, and it's our mind that imposes an order to them. When I look at the clouds, I see dragons and bunnies. I don't see randomness. We are programmed to see patterns. And think about observational conditions. When I'm tired, when I've been up late, when I'm driving, and it's nighttime, and there's a glare, my mind is trying to impose patterns on things. The world is not cooperating and giving me optimal viewing conditions. What am I likely to see? Funny shapes, maybe I hear spooky noises, see flashing lights, who knows, right? A normal street lamp or a weather balloon could turn out, to my mind, to look awful lot like what someone might say a UFO looks like. So our theory of constructive perception can not only explain human perception, it can also explain UFO sightings. That gives it broad scope. It can explain two things. The UFO theory can only explain one of them. So strike one against the UFO theory. So that's just how scope works. And we'll see a little bit of that through some of our examples. Simplicity is a big one. Simplicity basically means all else being equal, the simplest theory is usually correct. False theories get way too complicated too quickly. Here's how you can know, right? And I bet I can appeal to your experience on this one. Have you ever met someone who was a bit of a liar? Most liars tell stories that are far too complicated. Oh, yeah, so you see, I was trying to come see you, and then I got a flat tire, right? And then while I was changing the flat tire, a cop pulled up to me and said, "What are you doing?" And I had to explain to the cop, and then he read my plates, and someone had switched right? Like, it just gets way too complicated too fast, right? You know they're not telling the truth. Most people who are honest deliver simple, straightforward truths. It's liars who tell the overly complicated stories. That's also how they get found out, right? The more complicated their yarns are that they're weaving, the harder it is to track all the moving pieces that they need to track in order not to be found out. So, simple theories are usually true. Why would I explain something with a really complicated theory if I could explain it with a much simpler theory? This is also where flat earthers tend to go wrong. And I'm not here bashing the people that promote flat earth theory, right? Who knows why people promote the theories they promote. But if we just look at the theory itself, even way back as far as Copernicus and before and later than that, Galileo, there were people still working on geocentric or Earth-centered models of the solar system. And the way Ptolemy did it, the ancient astronomer, he said, here are some things that can't be explained on our Earth-centered view or even flat Earth view. And the way to do it is to assume that planets are moving in these little epicycles around a much bigger planet. They were spherical, so it's not completely flat Earth, but some of the geometry works out to be similar. But that was a really complicated story. That means every planet that's orbiting us on the geocentric model is in that orbit doing its own little circles. Of course, we know that planets don't just orbit nothing. That would violate the laws of physics. What object is it attracted to, and so on and so forth. But nonetheless, that was a really complicated theory. What if we had a simpler theory that could explain the same things? And we do, right? Copernicus's or Galileo's heliocentric model is much simpler, right? Planets just move in ovals, very straightforward. They first thought it was perfect circles, but we now know. But that being said, it's a much simpler theory. Simple theories are just those that make the fewest assumptions. And typically, if a simple theory can explain the thing we're trying to explain, we're going to prefer the simple theory. Okay, and the last one is conservatism. Other things being equal, a theory that fits with other things we have good reason to believe is the theory to prefer. It is not certain, so we have to lose the word certain from our vocabularies for this chapter, right? We would never say, how can you be certain that general relativity is true? I can't is the response, right? But I do know, given all the other things we know about how the world works, that theory fits with them and has broad scope, is relatively simple, and so on, right? It's fruitful, it's testable, internally consistent, and so forth. So when we have some explanation, if that explanation doesn't fit with what we thought or what we already know, we're going to be skeptical of that new explanation. Just for instance, right? Suppose that like here sitting on my desk is a pen and I leave the room and come back and my pen is gone. And someone says, it just floated out the window. You're not going to believe it, right? Well, I'm immediately skeptical. Why? Because I know gravity works, right? Gravity means objects don't just float out windows. They might roll off tables. Someone might pick up a pen. I know all the different reasons pens might disappear. Flying out the window doesn't fit with other things I have really good reason to believe, right? Objects don't just float away. Since I have good reason to believe those other things, I'm going to be skeptical of the new theory if it contradicts what I already have good reason to believe. So it doesn't mean we have to be dogmatic. It doesn't mean we can't believe in progress. It's just about skeptical. If I'm in some domain and a theory contradicts other things I really do have good reason to believe, then that's a big burden of proof that has to be overcome. Because they not only have to convince you in this case, they have to tell some news story about why we should give up all those other things. So if someone really wanted to believe, let's say, in a particular conspiracy theory, that conspiracy theory might also then require that we give up beliefs about chemistry, right? So suppose someone says, hey, I can turn lead into gold. Well, I know you can't, or at least to believe you can turn lead into gold is to then reject everything else we know about chemistry. That's a heavy burden. Not impossible, perhaps. It's just a heavy burden. If we're placing our bets on which theory or explanation is likely to turn out true, it will be the explanation that fits with things that we have good reason to accept. Okay, so let's do a quick big picture talk through. Once we have looked at competing explanations and we've compared the different criteria to see which theory is best, maybe one theory is testable and one isn't, or maybe one theory is simpler than another theory, or maybe one theory is more fruitful or conservative or has broader scope than some other theory. Once we start getting some reasons for why we should prefer one theory to another, we've not yet used inference to the best explanation. We're just debating which explanations are the best. But once we know that one explanation really is better than the alternatives, and we don't have to be certain here, but if we have good reason to think that an explanation is better than the alternatives, then we can deploy an inference to the best explanation to infer that that theory is probably, keyword, true. That is an inference to the best explanation. We will practice some of our criteria, but that being said, that will wrap up this short overview. You also have a chapter to read that covers this same material, and it should be the case that nothing I said here contradicts that. It's meant to summarize and help us think through that material from our text. So I hope you take a moment to take a look at that, and I look forward to seeing you in the discussion forum.